Good evening, everyone. On behalf of Electrical Department of SGS ITS family, I welcome you all to the webinar on a perspective on performance, power, and energy efficiency of GPUs. If you have any questions during the presentation, please type them into the comment box. I'll bring them up after the presentation. Now, without further ado, I would like to invite Dr. Arun Parak sir to introduce our eminent speaker, Dr. Sohan Lal Sharma sir.
Good afternoon, everyone. Good afternoon, participants. And good morning, Sohan. Because in India it is 4 o'clock, but Germany it is 12 noon. Okay. So it is my pleasure to introduce Dr. Sohan. Dr. Sohan Lal is a postdoctoral researcher at Technical University Berlin, mostly known as TU Berlin, Germany. He graduated with PhD in computer engineering from TU Berlin in 2019. His dissertation was titled Power Modeling and Architectural Techniques for Energy Efficient GPUs and was PhD. He won several grants, including HIPEAC ACM Travel Grant and HIPEAC Collaboration Grant. He has worked on several European Union and German government-funded research projects in the area of low-power computing on GPUs and runtime support for large-scale HPC clusters. He is interested in computer architecture in general and GPU architecture in particular. His broad research interests include power and performance modeling, performance bottleneck identification, memory system, and heterogeneous computing, approximate computing, applied machine learning, and GPU security. Before PhD, he received his master from Indian Institute of Technology, Delhi. Before that, he worked as a lecturer at Shri Mata Vaishnav Devi University, Katra, which was his first teaching experience that made him deeply passionate and excited about teaching and mentorship. So this is Dr. Sohan. I welcome him for today's lecture. Thank you.
Thank you, Dr. Arun Parak, for the introduction. My name is Sohan Lal, as just introduced by Arun. I'm a postdoctoral researcher at Technical University of Berlin and also did my PhD from there. So I invite you, welcome to my webinar on a perspective on performance, power, and energy efficiency of GPUs. GPU stand for graphics processing unit. As some of you might not be familiar with what are GPUs and in which scenarios we can use graphics processing units compared to a CPU. I have a quick high-level introductions to CPU and GPUs. A contemporary multi-core CPU consists of a few complex cores, and it has an intricate control logic, multi-level large caches which are connected to an off-chip DRAM. If you compare this to a CPU, then CPU has many small core. To give you a perspective, a latest GPU from NVIDIA, for example, can have more than 4,000 core. The caches in GPUs are very smaller. Essentially, if you compare like what is the per core cache available in a GPU to a CPU, it's very tiny. The control logic is also very simple. The DRAM has a high bandwidth DRAM in a GPU. Then the next question is like in which scenario we can use a multi-core CPU and versus a many-core GPU. I take a very simple analogy for that. If you look at this example, if you have to take a few people from place A to place B, then a car is very good for that. You can use a car. But if you have to take many people from location A to the location B, then a bus is much more efficient. It's much more efficient in terms of cost, and also faster than the car. Similarly, if you have a not so much parallelism, you can use a multi-core CPU. But if there is a massive data level parallelism, we can use GPUs. GPUs, as I said, stands for graphics processing units, and initially they were designed for processing only graphics application. But their massive computational power led to general purpose computing on them. And when I say general purpose computing, I mean the same kind of a computing that we can do it on a CPU, we can also do on the GPU. And today, the GPU accelerated computing is present everywhere. GPUs are in our smartphone, in our cars, in our desktop computers. They are present in the data centers, and of late also in cloud-based systems. So if the GPUs are so good, like they are present everywhere, then what are their problems? What are their challenges? Let's have a look at the power consumption of the GPUs. The figure shows the number of GPUs sold in 2017. In 2017, 2.1 billion GPUs were sold, and out of that, 17% were the GPUs in our PCs, personal computer, and our workstations. As my most of the research was focused on the discrete GPUs, I'll provide a further perspective on this 17%. The 17% of 2.1 billion is approximately 357 million GPUs, or discrete GPUs especially, sold in 2017, and that cost us around 89.25 million kilowatt hour, assuming that a GPU consumed 250 watt, which is a very typical number for a discrete GPU. And this cost us around 27 million euros per hour. Now, if we assume that we can increase the energy efficiency of the GPU just by 5%, then this can lead to this can lead to a saving of 4.5 million kilowatt hour, which corresponds to 1.35 million euros per hour. And this much is enough electricity to provide electricity to 11.3 million German household for 1 hour. These numbers are amazing. Of course, after looking at these numbers, one wants to ask how we can increase the energy efficiency of the GPU, how we can make them more energy efficient. To answer that question, we need to understand what makes GPU less energy efficient, because once the half of the problem is solved if we can understand what is the problem. So first we need to see what are their problems. This figure shows the achieved energy efficiency of GPU. Achieved mean when you actually run an application, and then what is the energy efficiency delivered by a GPU. The figure shows the achieved energy efficiency of the GTX 580 GPU. Is a bit old, also known as a Fermi architecture. On the x-axis is the IPC. The IPC is the instructions per cycle, and higher is better. For this architecture, the peak IPC is 1024. On the left y-axis is the energy per instruction in nanojoule, and lower is better. For this presentation, I'm only going to focus on this curve. If you can see that, each point or each dot that you see is a kernel or is a benchmark. It represents how much IPC and how much, for example, energy per instruction this particular benchmark has. For this study, what we do, we classify all the benchmarks or all the kernel that we have into two categories. We classify them into high performance category and the low performance category. All the benchmarks which have IPC greater than 50% of the peak IPC, we classify them as a high performance category, and all the benchmarks which have IPC less than or equal to 50%, we classify them as low performance category benchmarks. If we look at the further statistics, then the average IPC, we found that for the high performance category was 741, which is less than good, like more than 70% of the peak IPC is fine. But if you look at the IPC of the low performance category kernel, which have low energy efficiency, they have average IPC of 250. The 250 is even less than 25% of the peak IPC. So a lot of things are underutilized. If we look at the average energy per instruction, Then we have 0.27 nanojoule for the high performance category and about 2 nanojoule for the low performance category. If we put these number into perspective, then the low performance category is 13.5 times less energy efficient than the theoretical energy efficiency that is possible on this particular GPUs. If we put these numbers further into perspective, then we see that the low performance category is 7.5 times less energy efficient than high performance category. This is a huge difference, let's say, which is not favorable for the growth of high performance computing. We need more energy efficiency, and we are far away from exascale aim of 10 picojoule per instruction. Basically, the exascale aim of 10 picojoule says if we want to achieve exascale computing at an affordable power budget, then each instruction should not consume more than 10 picojoule per instruction. But to reach there, we have a gap of 200x. So we are very far away from that. If you ask me, if you are familiar with the GPUs, not all of you might be familiar with the GPU. The next obvious question that comes to your mind is, wow, this GTX 580 is like almost 10 years old now, is called quite an old architecture. How these numbers look on one of the latest GPU from the NVIDIA. So then NVIDIA Titan B, which is also known as the Volta architecture, is one of the latest GPU from the NVIDIA and is like 9.1 time more energy efficient than Fermi. Fermi is our GTX 580, that much more energy efficient. And if we assume that we run these benchmark on the Volta architecture instead of the Fermi architecture, and we assume that all numbers scale perfectly, although that will not happen, even if we assume all of these numbers will scale perfectly, then still the low performance category is like far away from the exascale aim of 10 picojoule per instruction. So the key message from this or the key takeaway message from here is that there is a huge difference between what is the theoretical energy efficiency of the GPU, what the GPUs say that they have this much energy efficient, and what is the energy efficiency which you actually get when you run your application or workload there. The gap is much, and we are also far away from exascale aim of 10 picojoule per second. And what we need to do, we need to bridge the gap between the theoretical and the achieved energy efficiency. So this was the overall motivation. So the overall motivation for my research that I have been doing over the last 7-8 years is to like, let's say, increase the energy efficiency of the GPU. Because it's an energy efficiency research, we need to have a power simulator. We need to have a flexible and accurate power simulator that can estimate the power consumption of the GPU. Because once we know the power consumption, we can estimate what is the energy efficiency and so on. So that's why we set this objective. Once we have the power simulator, what we want to do is we want to understand the bottlenecks. We want to understand the problems that cause low performance and low energy efficiency in GPUs. Then once you have understood the problems, or once you have understood the bottlenecks, of course, the next step is we want to come up with techniques that can improve or enhance the energy efficiency of the GPUs. See, so this was the introduction or the motivation for my work. The rest of the talk, I'm going to talk about how we develop the power model for the GPUs and how we use that power model or the power simulator to investigate the bottlenecks that cause low performance. And once we understand the bottlenecks or performance, we're going to propose a couple of architectural techniques to improve the energy efficiency of the GPU, and finally the summary and the conclusions. Please let me know along the way if you have any questions. I like to take them. So how did we develop the power simulator for the GPU? I just want to briefly say what can a power simulator do. Power simulator, if you simulate or if you run a benchmark on the power simulator with a particular GPU configuration, the power simulator can tell you how much power is consumed by your application. Let's say this is the main objective of developing the power simulator. So how did we drive the power simulator for the GPU that we called GPU Simpo? We use MacPad as base. I'm not sure how many of you know MacPad. MacPad is a CPU power simulator, basically a tool for estimating the power consumption of the CPU. We use MacPad as a base because there are a lot of similarity between a CPU and a GPU architecture. So we can reuse some of the existing infrastructure from there. However, since there are also significant differences, as I said very briefly in the beginning of the presentation, significant differences between the CPU and a GPU architecture. So what we do is we modify the MacPad and extend it with GPU specific component. And once we do that, we get a power model for the GPU. From this power model, what we can get, we can estimate the GPU area and the static power. Basically, the power consumption of a CMOS circuit has two main components: the static power and the dynamic power. The dynamic power depends upon the utilization of the circuit or the utilization of the components. To get an estimate of how much the components are utilized, we use another simulator, architectural level simulator, that can tell us, for example, how much caches are utilized, how much registers files are utilized, how much cores are utilized, and so on. This information we can get from an architectural simulator. So we use GPU sim, again another tool, another important tool for GPU research. We use this tool as a base, and then we extend this tool to generate your utilization. We call them activity factor, but basically they tell us how much the different components are utilized. Then we put these two together, and the whole infrastructures require GPU benchmark, the application whose power you want to estimate, and the GPU configuration, for which GPU you want to estimate the power consumption. Once you have that, then you can also get the dynamic power. So basically, GPU area, static power, and the dynamic power, you can all of estimate all of them. The key features of the power simulator that we developed are: it can estimate, or it can provide an estimate of the static power, the dynamic power, as well as the area. However, then the interesting feature of the simulator is that the power estimated is provided down to the component level. That means it doesn't tell you just like this GPU A consumed 200 watt. No, it tells you, yes, GPU A consumed 200 watt, but let's say 10 watt is consumed by the cores and this much is consumed by the caches, your network on chip, or the memory controller, and different components. So you can get an understanding of the power consumption of a GPU components at a very detailed level. That's the advantage of a power simulator. Then how do we develop it? This was a very high level overview of the tool, how we develop that. For developing the power model, following is a high level approach. We check if a component that we needs to model, does it exist in the MacPad. As I said, MacPad is the base for our whole work, for this power simulator. If the component already exists in the MacPad, then we reuse this component with proper parameters. For example, there was a power model for memory controller, and we just adapted it for the GPU case. However, there were several components which were missing, and for them we took a hybrid. In my personal experience and in my personal opinion, like 10 or 11% error is quite good and acceptable for conducting like architectural research in our field. That is good enough. Okay, so now what we had, we have the, let's say, tools, because we need everyone needs tool to work. So one, we already developed the power modeling, or we have a power simulator that we can use for further investigation. So we use this power model or power simulator to investigate the bottlenecks. How do we do that? I will again provide a very high level overview, and if you have any specific questions, we can discuss them later. So we took a lot of kernels or a lot of benchmarks, as you say. We divided them into two categories: the low performance category and the high performance category. The same as I discussed in the motivation. As the high performance category, according to us, is doing good, we didn't do anything with that, and we leave these kernels out of the study. However, the low performance category kernel, we further divide into two categories: low occupancy
and the full occupancy. The question is, what is an occupancy? As I said, that GPUs, they have many cores, right? I said if a latest GPU from NVIDIA can have 4,000 core. If it can has 4,000 core, we also need that many threads or even much more number of threads to keep the GPU busy. So occupancy kind of indicates how much occupied a particular GPU is. If a GPU, for example, can have maximum of 1,000 thread and only 500 threads are allocated, then it has a 50% occupancy or 0.5%. As occupancy is important to achieve high performance. For example, it doesn't make any sense to run one thread on a GPU and say one thread on a CPU. One thread on a CPU will be much more faster than running one thread on the GPU. Running one thread on the GPU is highly inefficient. We will not do that. So as a minimum occupancy is required, that's why we study if occupancy is causing any problem. So we further divided the low occupancy kernel into different categories. Basically, we have like three more categories which are known as CTA. CTA is the cooperative thread array or a group of thread in GPUs, or the register limited or share memory limited. What I want to say at a high level is, how do we decide that the low occupancy kernels can go into one of these categories? Depending upon the resource. These are the hardware resource in GPU, and one of them can limit the occupancy. And depending upon what resource is limiting the occupancy, we classify that kernel into that category. For the full occupancy category, since occupancy is not a problem because this GPU or these kernels have the highest number of threads that is possible. They are there. Since that is the case, we study if the high bandwidth utilization or the low coalescing efficiency or SIMD utilization is a problem for this category of kernel. Now, bandwidth utilization is like, or bandwidth is more or less clear. What is a coalescing efficiency in GPUs? As I said, GPU follow a single thread, multiple data execution model, and there is a group of thread known as a warp, and warp usually consists of, let's say, 32 threads. They always execute the same instruction on different data element. Assume that each thread requires 4 bytes of data,
and there is a group of thread known as a warp, and warp usually consists of, let's say, 32 threads. They always execute the same instruction on different data element. Assume that each thread requires 4 bytes of data from the memory. Then for 32 thread, 32 into 4 will be like 128 bytes. So basically, one load from the DRAM or one load from the memory can be 128 bytes for the whole warp, or for the whole 30 for this group of 32 threads. This is good. In this case, this is perfect coalescing efficiency of 100%. But all the threads might not access the data from. In general, for this study, what we do is we ask ourselves this question: does increasing the limited resources mean the resources that are limiting the occupancy or so on? If we increase these resources, can we increase the performance and energy efficiency? If we can increase, then how much we can increase? This is the question. So for this presentation, I'll just focus on the two categories. I'll just give you a very high level overview. What did we do with them? So first is the analysis of the low occupancy category, in particular the one limited by the CTA limited category. The table shows the kernels that are in this category, or the benchmarks. This shows how much IPC they have. This shows what is the CTA size. I'm going to talk about that, and what is the occupancy. If we look into this category, the average IPC is 371 for this category of kernel. There are many categories, and that is less than 37% of the peak IPC. So according to our study, this is very bad for energy efficiency. We need to have better. And the lowest CTA size is 64 here. If you look at, there are two kernels whose CTA size is 64, and CTA size basically tell us how many threads are in this block, or in how many thread in the cooperative thread array. And CTA is basically a unit of scheduling across different multiprocessor in a GPU. I'm again not sure if you know that, but a GPU has several multiprocessors, and the work is distributed across multiprocessor at the granularity of CTA. Now, how can a CTA size, which is in this case, let's take an example of 64, can limit the occupancy, can lead to occupancy of 0.33. Here is a simple calculation. The CTA size is 64, and for this particular GPU, the maximum number of CTA that you can allocate is 8. This is a hardware limit. You cannot have 9 because only these many hardware resources are available. And if you multiply them and divide by the maximum number of threads that this GPU can have, basically not the GPU, the one multiprocessor. The one multiprocessor can have 1,536 thread. If you do the math, we have only 0.33 occupancy or 33%. Very simple math can tell us that to achieve 100% occupancy, we need 24 CTA. 24 into 64 will be 1,536. Since we are not using the real hardware, because in a real hardware, you cannot change that. Because we developed our simulator, this is a simulator. In simulator, you can change the parameters. So we did change these parameters in the simulator and then study how does it affect the performance, power, and energy consumption. So this figure shows how does the different things get affected. Now, what are the key observation? The key observation is that one of the kernel MCO, for example, its performance almost doubles when we increase the occupancy. What does this show? That this kernel basically was performing bad, or it has a low performance, low energy efficiency because of the low occupancy. However, if we look at another kernel, BS is a Black-Scholes kernel, whose performance actually goes down instead of going up. The further investigation, we investigated this kernel further and found that this kernel is memory bound. And when basically we increase the occupancy, what does occupancy does?
And the decrease in the performance. If we look at a couple of other kernels, and it shows that they are below this bar. This bar tells us the occupancy on the right hand, the utilization for different benchmarks. Again, what are the key observations? That there are some benchmarks which have high bandwidth utilization, right? And there are some benchmarks which have very low coalescing efficiency. And as just discussed before, that can be very bad for the performance. And some benchmarks have very low SIMD utilization as well. So what is the key message here is that several kernels are memory bound, the one which have high bandwidth utilization, and probably also those which have low coalescing efficiency, because low coalescing efficiency can exert very high pressure on the memory hierarchy. That's why we think that the memory bandwidth optimization technique can significantly improve their performance. And by memory bandwidth optimization, I mean we can either effectively use the existing memory bandwidth, or we can try to increase the memory bandwidth, right? These are the two ways to do that. This leads us to our let's say third objective. Key observation work that there are some benchmarks which have high bandwidth to propose some architectural techniques to improve the energy efficiency of the GPU. Because now we have a better understanding of the GPUs. We have tools that can provide us information, and with the tool we gather some information about the bottlenecks. And now we want to use this information to do something useful. Let's have a look at it. What did we do first? The first is the efficient spatial locality predictor for GPUs that we developed. As I said before I go into the detail, that a warp can do a transaction of 128 byte from the off-chip memory or from your DRAM. But because of these scattered memory accesses, the whole 128 byte might not be used, because there is a lot of memory divergence, or a lot of memory accesses are scattered. This figure shows when we divide a 128 byte cache line or the memory transaction into 4 sectors, with each sector 32 byte, how many sectors are used on an average. Figure shows that only 80% of the time only one sector is referenced. And most of the time we are actually bringing 128 byte in our memory or in our caches, but we are only using 32 byte out of that. This is not good, right? So that's why we came up with a dynamic access granularity system, and which uses the spatial locality predictor. We have a predictor in the load store unit which can tell us how many sectors will be used, and then based on the predictor we only fetch that many sectors and not the whole 128 byte or 4 sector always. This technique gave us around 20% speed up over coarse grain accesses. Coarse grain accesses mean when we always fetch 128 byte. and this further has a speed up of 10% over the state of the art. Remember that not all will benefit from this optimization, but only those benchmarks which have low clustering efficiency, because they don't need whole 128 byte, but maybe only a couple of bytes or only one or two sector out of 128 byte. Okay, so this was one technique which we use to effectively utilize the available memory bandwidth. Then the second technique that we came up is we want to do memory bandwidth compression. Let's say we want to increase the effective memory bandwidth. The question is why we need them. Again, we know that several benchmarks are memory bound, and they will gain from the increasing memory bandwidth. And furthermore, the conventional ways to increase memory bandwidth. What are the conventional ways to increase memory bandwidth? You can have more memory channel on a GPU, but it's getting super difficult to integrate more and more memory channel on the GPU due to power consumption issues and the issue of number of pins and so on. Then, of course, the next question is, why do we need new technique? Because there are memory bandwidth compression technique. Why do we need new technique? The answer to that is the existing memory compression techniques exploit simple pattern, and they trade low compression ratio for low decompression latency. And the reason for that is GPUs are quite new, let's say relatively new. Especially the general purpose computing on GPU is only a decade old. But if you look at the CPUs, they are with us. The first microprocessor was designed in early 70s and so on. So CPUs are quite old. There are a lot of techniques available for CPUs, but not the same number of techniques available for the GPUs. So that's why we need to come up with new techniques for the GPU. The reason is then we ask ourselves a question: can we do better for the GPUs? Since GPUs can hide latency to some extent because they use massive multi-threading, they can switch to new thread when one thread or one group of thread is waiting for the data from memory. They can hide latency. This is not the case with CPU because CPU are very latency sensitive. If you increase the latency, their performance goes down. There are some benchmarks which have very low, are not that latency sensitive divergence. We proposed a bit complex entropy encoding-based memory compression technique for GPU. The advantage of this technique is that it has a higher compression ratio, of course, because it's complex, but it's also challenging because it's much more complex. It's not that simple. So I will briefly talk about how we tackled some of the challenges for the entropy encoding. The first challenge is what is the best symbol length for encoding? Because for entropy encoding, the compression or the effective compression that you can get depends upon what is the symbol length you use. So we basically experimented with the different symbol length. If you see just the averages, and we found out that its symbol length 16-bit symbol length provides us the highest compression ratio for GPU. The second important thing or important challenge about the entropy encoding is we need to estimate the probability of symbols, because once we know the probability, we will assign the lowest symbol or we will assign the lowest code word to a symbol which has the highest probability. But how do we find the probability of the symbol? So basically we used two techniques. The first one is the offline probability estimation. In an offline probability estimation, we do offline profiling of load and store, and this provides us the best probability estimate because we know all load and store beforehand. Unfortunately, the entropy characteristics of workloads or benchmarks are not always known in advance. That's why we might not be able to use this method to estimate probability. So we come up with another methodology known as online probability estimation. How do we do online probability estimation? We run the benchmarks, and in the beginning, we do sampling. For some duration, we do sampling, and during the sampling, we record different symbols and their frequency. Once we have the symbol and the different frequency, we can come up with a coding table to do the compression and so on. The two important challenges that we that we have to tackle for online probability estimation is like what is the best sampling duration until when you should sample and then start doing coding, because when you are doing sampling you are not doing any compression, so basically you are wasting time that period. So this is very tricky. And the second question is, what is the suitable number of most frequent symbols or most frequent value that you will use? Because when you are doing sampling, we may encounter 1 million different symbol, and 1 million different symbol, we cannot store it in a table because it's not hardware efficient. So we have to answer that question. Without going into detail, I want to say that we found that if we sample for 20 million instruction, that is the best that we found for GPUs, and only 1K or 1000 most frequent values were enough to build the coding table. The third challenge that we had to design a good compression technique, memory bandwidth compression technique for GPU, is how to keep the decompression latency short. Of course, as I said, the GPUs can hide latency to some extent, but let's say if there is a too much increase, the too much increase can also lead to low performance for GPU. So we want to do some parallel decoding so that we can reduce the decompression latency. But parallel decoding is not easy for entropy encoding based technique if you are familiar with that. The challenge here is because when you are doing decoding, the code words are of variable length. So you don't know the next symbol until you have decoded the previous symbol. There is no way to know. That's why the decoding in an entropy encoding is serial. To come over this issue, what we do, we use like pointers. We store explicit pointers in the beginning of the block to the memory locations or to the code words from where we want to do decoding in parallel. But this parallel decoding does not come for free. It has a cost. There is a trade-off between the compression ratio and the decompression latency. Because with parallel decoding, we are bringing the decompression latency down, but at the same time, the compression ratio is also going down because we are storing extra metadata in a block, right? So we with the experiment figure it out that 4-way parallel decoding is good for GPUs, and that give us the highest performance. Let's look at some of the results that we got by using online probability estimation. This figure shows the compression ratio for BDI. BDI is a base delta immediate compression technique, like one of the state of the art compression technique. FPC is a frequent pattern compression technique. They are very simple, but if you look at in this let's say averages only, then E2MC or the entropy encoding based memory compression techniques can provide us 35% higher compression ratio than BDI and 26% than the frequent pattern compression. If we look at the speed up using online probability estimation, I'm again just focusing on the average. If we don't do parallel decoding to decrease the decompression latency, then basically E2MC or the entropy encoding technique is slower. The reason for that is the higher decompression latency. To just give you an idea, E2MC required around, I guess, if I remember correctly, around 80 cycles to decompress a memory block, whereas FPC require around 5 cycles and BDI just 1 cycle. So they are very simple, but as I said, their compression ratio is low. However, if we use parallel decoding, then we can get a 17% speed up with 4-way parallel decodings, and which is 5% higher than the BDI. And this gives us to our leads us to our overall motivation. Our overall motivation was to increase the energy efficiency. So by this technique, we can reduce 11% energy and 24% EDP by using online probability estimation. But one thing you get from this is that the increase in speed up is not that much. This is the impression that I also have. So then we try to figure it out why we are not getting that much speed up. So basically, we found that the lossless memory compression techniques have low effective compression ratio. How? Let's take an example. So, for example, your uncompressed block is 128 byte, and we divide it into 32 byte. And 32 byte is like an important granularity. We'll see what is that. When we do compression, the 128 block can be compressed to any size, right? This is possible. For example, if it is compressed to 36 byte, let's assume it's compressed to 36 byte, then we have a raw compression ratio of 3.6x, which is calculated by 128 divided by 36 byte. Very simple calculation. So very impressive compression ratio. But what happens in reality? from your off-chip memory or from your GDR or DRAM, it's not possible to fetch 36 byte. There is no way to fetch these 4 byte, because from the DRAM you can always fetch in the multiple of burst size, and the burst size, also known as memory access granularity, is a typically 32 byte for the GDDR or your DRAM. That means you don't fetch actually 36 byte, you actually fetch 64 byte. There is no way to fetch lower. So then what you do, we end up with the low effective compression ratio. So the compression ratio, actually you only have 2x instead of 3x. So this was the one of the underlying reason why we were not seeing so much increase in performance. Then what we do is, this was a dummy example, then we run a lot of benchmarks for different techniques. These are the different techniques: BDI, frequent pattern compression, CPAC, and one developed by us, E2MC. And again, if you're just focusing on the averages, what we see, the second bar which shows the effective compression ratio is always lower than the first, and on an average around 20%. Excuse me. So what we found, that many several lossless compression technique, basically they have a low effective compression ratio due to this large memory access granularity. And then what we do with that, we try to further investigate in detail, because this is what you do in a research. You want to reach to the bottom of the problem. As I said in the beginning, once you understand the problem, you can propose solutions. So what we try to do now is, we try to understand the distribution of the compressed blocks. This figure shows that it shows the number of bytes above memory access granularity. Like here, if you see this example, then for example, this particular case, when I said 36 size, compressed size, has 4 byte above the memory access granularity, right? So this axis shows how many bytes above memory access granularity. The left y-axis shows what is the percentage of block, how many percentage of blocks have 4 bytes, for example, above memory access granularity, and the color indicates number of samples, or for simplicity, you can say number of benchmarks. The quantitative analysis shows that distribution does not favor any specific size above memory access granularity. The distribution is quite uniform, which is expected. However, if we focus on this area, let's say, what we see, that there is a significant percentage of blocks that have a few bytes above memory access granularity. Let's say if we focus on this region, then around 20% of the blocks have only 4 bytes above memory access granularity, and this could be the case between 8 to 12 benchmarks. So what we thought about that, why not, instead of fetching few bytes from the DRAM, why not we can selectively approximate these few bytes and make them a multiple of the memory access granularity. This is exactly what we did with a selective lossy compression or selective lossy approximation. But again, it was not at all easy, because challenge is to find how many symbols we should approximate to decrease the size to a multiple of memory access granularity. As you remember, that when you compress a block, then you have a code words, right? You don't have symbols anymore. You have the code words, and the code word, if you approximate, there is no way to go back to the original symbols. That's why we cannot approximate the code words. Since it was not trivial to find which symbols to approximate, in one of the simplest technique, what we do, when we figure it out that a particular block has few bytes above memory access granularity, then basically we quantize that whole block by using simple quantization, whole block. But remember, not all blocks, only those blocks which have a few bytes above memory access granularity, and then this can be specified by a programmer or by the designer, how many bytes you want to approximate. In one of the more complex technique, we actually first figure it out how many symbols exactly need to be approximated, and then only approximate those symbols and not the whole block. These have interesting trade-offs, which again I'm not going into detail. If we look at the results, what we gain from this technique, then this technique can give us a maximum speed up of 35% for 64 byte memory access granularity. The key advantage of this technique is the maximum accuracy loss is 1.8%, and on an average, it's less than 1%. And I just want to state here, the state of the art, when we were doing this work, the state of the art assumes like 10% error is acceptable, and 1% is almost nothing compared to that. Again, if we look at our broader objective, we reduce 8.4% energy and 18.2% EDP. And this reduction is on top of E2MC plus whatever you can gain from E2MC plus after applying this technique. I think I'm close to my summary and conclusion for this webinar. What I want to say is that GPU accelerated computing is everywhere, right? GPUs are now present everywhere. The reason for that is they have a highly computational power. They are massively multi-threaded. But what we figured out that there is a big gap. There is a very big gap between the theoretical and the achieved energy efficiency of the GPUs. Therefore, we identified several bottlenecks that can lead to low performance and low energy efficiency in the GPU. We figured out if we increase the occupancy, it can increase the performance and energy efficiency. On an average, let's say 18% and 12%. But we also figured out that just increasing the occupancy is not enough. For the full occupancy kernels, we show that they might be limited by memory bandwidth, coalescing efficiency, or SIMD utilization. For this particular part of the research, my bigger conclusion or bigger message is that no single architectural component is enough to focus, but we need to consider multiple of them in a holistic way to increase the energy efficiency of the GPU. By this, I mean, for example, just increasing the occupancy is not enough. We need to look at all components together to increase their performance and energy efficiency. Once we found the bottlenecks, we show that a dynamic memory access granularity, which has a combination of coarse grain and fine grain accesses, basically is quite useful for effectively using the available memory bandwidth in GPU, and it can result in higher performance. Then we show that we proposed a couple of memory bandwidth compression techniques for GPU, and we show that memory bandwidth is a promising alternative to increase the memory bandwidth. When I say alternative, you can also use the wider channels, but they are more expensive. The E2MC, for example, delivers higher compression ratio, 35%, and speed up over state of the art, provided its key challenges are addressed properly. Then we show that the state-of-the-art lossless compression technique, they have low effective compression ratio, or they suffer due to large memory access granularity. We show that MAG-aware selective lossy compression can provide speed up to 35% on top of E2MC with less than 1% average error. If we combine these two techniques, we can save around 19.4% energy and 42.2% EDP. Remember, in the very beginning, when I motivated the presentation, I said that 5% increase in energy efficiency was enough for about 11 million German households. And then you can imagine, or you can think, what does 19.4% energy efficiency can do us. For this category of the architectural research, what is the key message or the key takeaway? That we need to effectively utilize the memory hierarchy. It is very important. We show this by designing a dynamic memory access granularity system. We show that the memory bandwidth compression, it will play a significant role in the future, especially when it's hard to scale the DRAM bandwidth. And on top of that, we have these days big data. We have a lot of data, but the data has a lot of redundancy. A lot of redundancy means the opportunity is there for doing compression. And furthermore, with the benefits of process scaling, if you are aware of that, the benefits from the process scaling are nearly coming to an end. And in my opinion, now the more onus or more responsibility is on the architects and programmers to keep the wheel of performance scale spinning at least in the near future, until we have alternative technologies to deal with that. We also developed a power simulator in the very beginning of this research. In my opinion, is also a very useful tool for conducting GPU architects and programmers to conduct research in this area. I would like to thank AES or this TU Berlin where I work. Of course, this work is not just done by me, but also my collaborators and other co-authors. I also like to thank European Union. This work was funded through a TU project known as low power parallel computing on GPU. I would like to thank SGSITS, Professor Rakesh Saxena, the director, the Professor H.K. Burma, the head of EE department, of course, my friend and coordinator, Dr. Arun Parakh and Dr. Shilender, and all other people who gave me the opportunity and helped to set up this nice presentation. I thank you all of you for attending my presentation. And if you have any question, I would be very happy to answer them. Thank you very much.
Thank you, sir. Thank you, sir, for a very informative session. Now, we go ahead and take some questions, sir. Yeah. First question is, can GEM5 support GPU?
GEM5, yes, it's a very good question. GEM5 basically was originally only designed for CPUs. So basically you can only do a CPU work. But of late, if I remember from the top of my head, there is also a GEM5 GPU where basically some researcher from the University of Wisconsin in US, I think they put together GPU, the GEM5 and GPU together, and by using this simulator, basically you can do the full system simulation. The tools that I used, this GPU sim or the power simulator that we developed, it is specifically only for GPU. The CPU part of the application still runs on a real hardware, on a real CPU. But by using this GEM5 GPU, which is a combination of these two tools, I think you can simulate both the CPU and GPU.
Yes, sir. As architecture of GPUs are evolving regularly, but is upgradation in GPU simulator also happening simultaneously? How researchers can explore the latest architecture on older simulators?
Yeah, I think this is also a very interesting question, and unfortunately, the simulators, at least in the academic field, all the tools that we academicians use are, I think, not that upgraded as we have the industry tools. For example, what is available with the NVIDIA, Intel, or some AMD, our tools are not that updated. But yes, I think because the research community is also, let's say, these days quite large, and a lot of people are collaborating, for example, over GitHub and so on. And we are seeing that this trend is changing, that the tools are still lagging behind, in my opinion, but they are catching up. They are also being updated time to time. But conducting, I think, the architectural research, in my also opinion, nothing much is changing. Let's say from one generation of one architecture to the another architecture, there are not so big micro architectural changes that you cannot use the existing tool. We can use them and they are still useful.
Yes, sir. What are the future researches on the concept of GPU architecture rather than on specific GPUs of particular brands?
Yes, so I think from the, as I said, from the architecture point of view, as I said, the in my opinion, in the last years or last couple of decades, most of the performance benefit that we were getting basically from the process node scaling. The process node was becoming smaller and smaller, and that was already giving us a lot of performance advantages. And I think other changes that was happening at the microarchitecture level, even if they were not too much, we were still fine for that. As we know that the process scaling is coming to an end, I think now is very hard to get or see those benefit from the process scaling. That's why the more responsibility on the architecture to improve the microarchitecture. I was in one of the highest rated microarchitecture conference known as the Micro a couple of years back. And there was a big research team from Intel that was present there, from Intel Bangalore. Guys were also there. They have a very good research group there. And I asked them this question there, like, oh, come on, see, if you talk about one of these accelerator, like machine learning and so on, people are publishing paper there with like a 4x increase in performance, 2x increase in performance, very easy. But if you're doing like a CPU architecture, microarchitecture research, the gain is not much, 2%, 5%, 10%, and then it's very hard to publish that kind of research. The guy at that point have told me that even if you can improve the microarchitecture, that gives us 1% increase in performance. He said that's the birth of millions of euros or millions of dollars for Intel, and they will welcome that research that can improve the microarchitecture to even 1% increase in performance. So that's why I think it's time again, at least for some time, to focus again on the microarchitecture.
Yes, sir. Is there any research possible using GPUs as main processor in the computer system?
GPUs are still as a co-processor. You have to use the CPU as a main processor. CPU is the master, I would say, because we are still not running any OS or any operating system that can do scheduling on the GPU and so on. So GPU, at least for the near future, I see still it as a co-processor.
So which language is best for working on real GPUs of NVIDIA, OpenCL or CUDA?
I will take it a little bit further. I think CUDA has the advantage that it gives you very good performance for the NVIDIA, and OpenCL is portable, that let's say you can run it on once you write the program, you can run it on NVIDIA, AMD or Intel GPUs. But there is something new coming up. I don't know if you knows that. There is a open standard called SQL. I don't know if you heard about that. It's very recent. And basically, if you write your code in SQL, that code you can run not just on any GPU, but also CPU and including FPGAs. And I recently came to know that especially Intel and so on, they're putting a lot of money behind that. And in future, probably SQL going to, I'm not sure, but I think it's going to take over OpenCL or CUDA. This is too early to say, but it's a catching up.
Yes, sir. Does configurable cache memory helps in lossy compression during memory access for energy efficiency?
So see, in general, the compression can be used anywhere in the caches also, or in the memory in the memory hierarchy. So the research that I did, I have these techniques integrated in the memory controller. So basically, we're doing only compressed transfer between the off-chip memory, which is your DRAM, and your on-chip memory. We were not really applying it to the caches. But yes, I think memory compression can also be applied to GPU caches. As I said, they are not that much latency sensitive. That can help.
Thank you, sir. It looks like we have covered all our questions. Now, I would like to call Dr. Shailen Sharma, sir, for vote of thanks, sir.
So your phone is muted, I guess. So your my microphone is muted.
Shailen, sir, mic, sir, your mic. Sir, open your mic, sir.
It happens. Again muted.
Hello.
Yes.
Now it is
yes,
okay?
It is audible.
Okay, thank you. So my part is to go for the vote of thanks. So first of all, I thank you very much on behalf of the Electrical Engineering Department, SGSITS, to our speaker of the today, Dr. Sohan Lal Sharma, for giving such a useful and nice talk today. I hope all the participants have enjoyed this session and they learned. I really enjoyed your session, Dr. Sohan. And what I guess from your lecture that you have condensed the information of some of the latest book in your 1 hour session.
Yeah, yes, that's right.
So it's a great, we're really thankful to you. Yeah. It's a wonderful session delivered by you. I thank you all participants who have patiently associated with us, and they have raised a very genuine and good questions to Dr. Sohan. So I think he appreciates all these questions, those who have communicated by our participant, and then our anchor has told to you. definitely to organize such kind of event, lot of processing is required, and we are thankful that we have a very good leader with our institute, Professor R.K. Saxena, who is our director, who has encouraged us to organize such kind of event, and then our head of department, Professor H.K. Verma, who has provided all such facilities and motivated us to organize such a series of webinar. Just for the information of Dr. Sohan, I would like to express that this webinar series in the institute, in the department, in institute, it is started from around a couple of 10 days back. But in our department, we have started this activities from 9th of this June, and this session will continue till 16-17. So you are one of the speaker, and that I hope our participants are really enjoying, and they will learn a lot from the outcome which you gain from your 10-year experience you have delivered in 1 hour. We really appreciate these things. I would like to express my sincere thanks to all our team, all our faculty members, those who are continuously associated to make such kind of events successful. So congratulate all the teams. I would like to thank all our volunteers, those who are continuously promoting such kind of event, and they are registering many participants, and they are organizing the other activity of this event. At last but not least, we are thankful to all other members, those who are directly or indirectly associated with this activity. Thank you very much. Pinky?
Yeah.
Yes, sir. Thank you, sir. Thank you, everybody. We appreciate you being here. Kindly fill the feedback form given in the WhatsApp group. And thanks again for joining us. And we'll see you next time. Thank you so much.
Thank you. Thank you very much. Bye.
Thank you.